Hello friends, welcome to Susan and John MathTube. In this video, let's discuss about volume integrals and Gauss Divergence Theorem. And in this video, we will make it very compact. That is, we will learn Gauss Divergence Theorem, and when we work out problems in Gauss Divergence Theorem, we will learn volume integrals. But the proper way of learning this topic is, first you have to be perfect with volume integrals, then you go for the shortcut method called Gauss Divergence Theorem. Anyway, Gauss Divergence Theorem is a connection between volume integrals, that is three-dimensional integrals, and surface integrals. And remember, surface means three-dimensional surfaces. It can be the surface of a sphere, it can be the surface of a cube, etc. etc. Earlier we learned about Green's theorem. You might have watched the last few videos in line integrals and Green's theorem, where we connect line integrals with surface integrals, but that is two-dimensional surface. Now here we connect volume integrals and three-dimensional surface. Anyway, in your exam they may ask state Gauss theorem. And whenever they ask a statement, you should write the statement properly. You cannot add your own words and write statements. So you can study that proper statement from your book. Anyway, I'll write the last part of Gauss theorem, the conclusion. That is, the surface integral f dot n ds is equal to the volume integral divergence of f dv. So this is the conclusion of the theorem, and there are many conditions in exam. When they ask statement, if you write only this much, you are not going to get marks. It will define all the conditions properly. Okay, and I hope you still remember to find divergence from your second semester. For those who do not know, let's say we have a vector function f1i plus f2j plus f3k. Then divergence of f is denoted by del dot f and is given by the partial derivative with respect to x of the I component plus partial derivative with respect to y, j component, plus partial derivative with respect to z, k component. Okay, and talking about surface integrals, we have to evaluate f dot n cap ds. Now remember, f is the given vector and n is the unit normal vector, the outward drawn unit normal vector, and n is given by the gradient of the function. I hope that's also from your vector differentiation from your first semester or second semester. So n is equal to gradient of phi, and n cap will be grad phi by mod grad phi. Okay, when we work out problems, we'll go through it, and then I hope you know how to take dot product. Okay, now this is the most important thing. Look at this. ds is actually calculated by dx dy by mod n dot k, provided you're going to project our three-dimensional surface on the xy plane. And ds will be dy dz by mod n dot I, provided you're going to project it on the yz plane, etc. etc. Anyway, if you want to understand this properly, we have to do one problem. Okay, so let's start with a very simple problem, and that's a problem of a cube. So please write, verify Gauss Divergence Theorem for the function f is equal to 4xz into I minus y square j plus yz into k over the cube bounded by x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0, z equal to 1. Okay, that's it. So the first thing you have to do is you have to write by Gauss Divergence Theorem. So you can write the statement of Gauss Divergence Theorem and say by Gauss Divergence Theorem we have this. We can either start from the right side or the left side. Anyway, I'll prefer the right hand side. So the right hand side is a triple integral and the limits are already given. You can see that the cube varies from 0 to 1, 0 to 1, 0 to 1. So x varies from 0 to 1, y varies from 0 to 1, z also varies from 0 to 1. Okay, so this is our cube and you can see that when we do three-dimensional integration and when we have a cube, things are very easy because it's straightforward. X varies from 0 to 1 at any point, you can check at any point. Remember, the variation of x means red color axis, variation of y means green color axis, and variation of z will be blue color axis. So you can see at any place parallel to the x-axis, it varies from 0 to 1, 0 to 1, 0 to 1, 0 to 1 uniformly. And that is an advantage of cube. Later on, when you learn about cylinder or when you learn about a paraboloid, etc., or maybe a parallel pipe, etc., things may be different. But in the case of a cube, it's the same. Even in parallelly piped also things will be same. But in cylinder, point to point, the value will be different. Okay, so let's go for the right hand side. Okay, now look at this. I'm going to write the limits x is equal to 0 to 1, y is equal to 0 to 1, and z equal to 0 to 1. And the function is divergence. So we have to calculate the divergence first. So I'll write divergence of f. It's very easy to calculate. Look at the first component or the I component and differentiate it partially with respect to x. Plus look at the y component and differentiate it partially with respect to y. And look at the last component and differentiate it with respect to z. So that will be 4z minus y. Okay. Now I'll plug in 4z minus y. Okay, we'll start integrating from x, y and z. So I'll write dx first because it will be easy to integrate this way. First I was planning to integrate with respect to z, but that will make things more complicated. This will be more easy because there is no x term. The terms will be more compact. So I'll integrate from x, y, z. So the order is dx, dy, dz. Okay, now this is from multiple integrals. You can perform this integration by treating y and z as constants. Z equal to 0 to 1, y equal to 0 to 1. Okay, now look at this. I'm going to integrate with respect to x. So this 4z minus y becomes a constant. And integral of dx will be x within the limits 0 to 1. Now integrate, this will become 1, and that is the advantage of differentiating from x, y and z. Now we don't have any more advantage because both the variables are present. Okay, now we are going to integrate with respect to y. So this is a constant. So the 4z is a constant. So we get 4z into y. And it's good to put the limits there itself, 0 to 1, minus y square by 2. And it's better to put the limits there itself, 0 to 1. So we get this will become 1 and this will become 1 by 2. So we end up with integral z equal to 0 to 1. Now integrating with respect to z, what will you get? 4z square by 2 Now you plug in that upper limit. So this and this will get cancelled. So you can note the right hand side is equal to 3 by 2. So what's the answer for the right hand side? 3 by 2. Okay, so the right hand side is 3 by 2. And this is actually one advantage of Gauss theorem. You can see that when we evaluated the right hand side, we had to evaluate it only once. But now we are going for the surface integral. And the surface integral depends on the surface. For example, this cube is made up of 6 surfaces. Look at this. One on the top, on the bottom, and the 4 sides. So total 6 surfaces are there. And that means we have to evaluate the same integral 6 times. Anyway, in the case of the cube, things are very easy because cube has plane surface as their covering. But if it was a cylinder or if it was something else, it would have been very hard because it has a curved surface, so the normal will be different at every place. Anyway, remember the red axis is the x-axis, the green is the y-axis, and the blue is the z-axis. Okay, I'll start with the surface. I don't know whether you are able to read this or not. HEDA, or let's call it, I think I have to make my cube a little bit bigger. It is 1 unit only, but yeah, I think you can see that surface. Okay, so now let's take it back to their original position. Yeah, so this is ADHE. Okay, so I'm going to write surface 1 ADHE. Now look at this. We have to evaluate F dot n cap ds, and since this is a plane, ds is parallel to this. So what do you call, our n cap will be very easy to calculate. In 1 second I'll tell you what is n cap. Can you see that this surface I'm talking about, I think you can see, I'll change the color. Okay, I'll put it kind of like green. Okay, now look at this. The green surface is actually parallel to the x-axis. So imagine drawing normal at any point on this surface. It will be always be parallel to this. That's a property of a plane. And n cap will be I vector. So remember, n cap will be I. At the same time, okay, I'll leave some space. We have to do more calculations. If you consider the surface just behind this, okay, I'll do one thing. I'll make that surface green. Okay, so you can see that the 2 green surfaces. Now you can see that the red axis is parallel to the normal. Imagine drawing normal at any point on this side. It will be parallel to the negative x-axis, and that means for surface S2, that is a surface opposite to ADHE, n cap will be minus I cap. Now I'll go down S3. S3 I'll take top and bottom. If you look at the top one, it's very clear. You can even see the normal at the end. It is what do you call the z-axis. So that will be K. So what will be the outward drawn normal? K. And if you look at the one below, look, this one, this surface beneath it, it will be minus K. And for the other 2 surfaces, it will be J and minus J. That is obvious. Okay, so let's start the first surface. Now F dot n, that will be, where is F? 4xz I minus y square j plus yz into k. There is an advantage when you take dot product with I or j or k. The advantage is you can distribute this dot, and I dot I will become 1, j dot k and j dot I and k dot I will become 0. So the answer is 4xz, because they are mutually perpendicular. J is towards the y direction, I is towards the x direction. They are at right angles. Similar is the story with k. Okay, so f dot n is ready, and now ds. And ds will be, let's take a look at the cube. Okay, so I'm going to project it on YZ plane. I'm going to project it on YZ plane. I think you can see the reason. It's easy to project it on the YZ plane, and we are going to get dy dz by mod n dot I, and that will be I dot I, that is dy dz. There is another way of interpreting this. Look at the green part of the box. Here there is no more x movement. This part is fixed at 1, right? There is no x movement, means we have to move in the x direction. In the green surface, we can move up or down or sidewards, but not in the x direction. So that explains why ds becomes dy into dz. Anyway, combining all these things, double integral in that surface 1 becomes z equal to 0 to 1. F dot n is 4xz, and ds is dy dz. And now you can evaluate this integral by yourself. First you do with respect to y. So you're going to get integral z equal to 0 to 1, 4xz 0 to 1 dz, and that will be 4xz. This will become 1. Dz. We have to change one more thing. There should not be x here. Remember, the value of x is fixed at 1. You can see this picture. The value of x is fixed at 1, because x-axis means the red color axis. So you can look at the point A. The value of x is fixed at 1. So x equal to 1. So you can replace this with 1. You should have replaced it here itself. It is 1. And that gives 4z square by 2, 0 to 1. So the final answer will be 2. So now we need to collect everything. I'll write it here. S1, the integral value is 2. Now for S2, I will recommend you to take the side opposite to it. So the outward drawn normal is what you call parallel to the negative x-axis. So I am going to write S2. You can write the name of the surface. It is CBFG. Okay, you can write the name. Anyway, most important part, n cap equal to minus I. And the x value is fixed at 0. You can see that. And the movement is y and z. So ds will be automatically, what is that? dy dz. And you can calculate f dot n cap. F dot n cap will be minus 4xz because of this minus. Now we are ready. So surface integral S2, that will be integral. So the movement is what you call z equal to 0 to 1, y equal to 0 to 1, minus 4xz dy dz. But look at this. What is the x value? It is 0. So this value will be 0. So S2 0. Okay, now what we do is we go for another surface. Let's call it S3. Okay, I'll do one thing. I'll make it blue in color for you. Now look at this. The blue surface, namely the top of the box, the roof of the box, has normals parallel to z axis. So n cap will be k. And you have to understand one more thing. There is no movement in the z direction. So z is fixed at 1. Because the roof is fixed, right? The roof cannot go up or down. But you can walk on the roof. Imagine you're standing on the terrace or the roof of your building and you can walk. But you cannot go up. You cannot go further up. You're on the topmost floor. Okay. So z is 1. And ds will be, can you guess what will be ds? Actually, we are projecting on the xy plane, so it will be dx dy. Or you can go through the formula method, it's up to you. Now, f dot n. Now look at this, since it is k, I am not going to write the story. I will just look at the question, that is the function, the given function. And I will take the last component coefficient. So that will be yz, right? So we start with double integral S3, that is the roof, and that will be double integral. I'll write x inside, x equal to 0 to 1, y equal to 0 to 1, y into z. But we have a surprise. What is z value? 1. And now you put upper limit and lower limit. That will give you 1, then y square by 2. Final answer is 1 by 2. You can show steps in exam. Anyway, I will go back to my collection. So S3, 1 by 2. And S4 will be equal to 0. Can you tell me why? In S4, what happens is, I'm going to take the bottom, the floor of this thing, the bottom. The bottom means z will be 0 and n cap will be, so let's say S4, that is the bottom part. So n cap is minus k because it is, the normals will be moving in the negative z direction. And when you take dot product, you're going to get the same thing but negative. So f dot n will be minus yz. But z is 0, z is fixed at 0. So this is going to be 0, so the integral value will be 0. But in exam, make sure you show steps. So S4 is 0. Now S5 means the remaining sides. So I'm going for the remaining sides. Okay, you can see that this is parallel to the, what do you call, y-axis. Okay, the name of the side is CD, what do you call, GH. The change will be in X and Z. I'm sorry, this is J. It is parallel to the y-axis. Please correct it. It is J. F dot n will be the J component. And what is the J component? Check the function. Yeah. So that will be minus y square. Okay. So we are ready for the fifth integration. Minus y square, z is changing from 0 to 1, x is changing from 0 to 1, and dx dz. I put z first, so we should put z first and then this second. Integrating, you will get minus 1. And of course, the last integral s, what you call 6, will be equal to 0 because n cap is minus j, and you have one more thing, that is the y value will be fixed at 0, and f dot n cap will be y square, and it will be 0, and if this is 0, the integral value is 0. Okay, so that's it. So I'll write my collection. So S5 is minus 1 and S6 is 0. Now what we do is we add all these things. So the surface integral value or the left hand side becomes 1 by 2 plus 2 plus 0 plus 0 minus 1 plus 0, and that will be, is a calculator, 3 by 2. Okay, that's it. So this is one very easy question, the cube. But in examination they can ask cube, tetrahedron or cylinder. Normally this is what they ask. Anyway, I'll be back with another video very soon. So till then, bye.